Hi everyone, I am Burak Bilal Bozkurt. I am studying at Bilkent University. My major is Industrial Engineering, and today I will be presenting to you my Physics 102 laboratory project. My project is about Faraday's law of induction, and the objective of this experiment is understanding the relationship between electromotive force, radius of a coil, and number of loops.
Before diving into the experiment, let's go over the materials I used to carry it out. This setup was relatively simple, yet effective for demonstrating Faraday's law of induction. First, I needed copper coils with varying properties. For phase A, I used coils with the same radius of 3 cm but different numbers of turns, 10, 50, and 100. For phase B, I used coils with a constant turns 20, but varying radii of 3 cm, 6 cm, and 9 cm. To generate a change in magnetic flux, I used a magnet, which was dropped through the coils from a consistent height to ensure uniformity. For measuring the induced electromotive force, I used a multimeter, which was connected in series with the coils using crocodile cables. These cables made it easy to connect and reconnect the coils as needed during the experiment. And these are the coils for my project. This is my basic setup image of my experiment. My experiment divided into two phases. One of them is phase A and the other one is phase B. This is phase A. In phase A, I focused on the number of loops, 3 coils with the same radius but different number of turns, 10, 50, and 100, were connected in a series circuit using crocodile cables. A multimeter was added to measure the induced EMF. The key was to keep the magnet's velocity consistent, so it was always released from the same fixed height to ensure a uniform change in magnetic flux. Now, this is phase B. In phase B, I investigated the effect of coil radius. This time, the number of turns was kept constant at 20, but the coils had different radius, 3 cm, 6 cm, and 9 cm. Just like in phase A, I used a fixed height for releasing the magnet to maintain consistency in the results. Now let's look at the results. In phase A, where the radius was fixed, the EMF was increased as the number of turns increased. For example, with 10 loops, the EMF was measured at 0.0023 volts. And these are the results of phase B. In phase B, with a constant number of turns but varying radius, a similar trend was observed. For instance, for a radius of 3 cm, the EMF was 0.0032 volts. This shows that a larger radius enhances the magnetic flux, leading to a higher induced EMF. And this is the plot of phase A with worst line and best line. And this is the plot of phase B. Now let's look at the error percentages of both phases. In phase A, the error percentages were relatively small at around 2.61% for coils with 150 turns. This could be due to slight variations in coil winding or minor inaccuracies in multimeter readings. Now let's look at phase B. The error percentages were more noticeable. For the largest radius of 9 cm, the error reached 15.28%. These larger discrepancies were likely caused by the manual release of the magnet, which made it difficult to maintain a consistent velocity as well as imperfections in the coil structure. And so, this is the end of my video. Thank you for watching and listening to me.